Hey guys, welcome to another video on backpropagation for neural network. And in the previous video we talked about what a neural network is and how you can use the concept of backpropagation to train your neural network. So this video assumes that you have the conceptual understanding of backpropagation and neural networks. So if you don't know what a neural network is, or if you don't know how backpropagation works, just go back to my previous video and check it out. And yeah, with that being said, we'll just start off with writing Python implementation to use backpropagation and build a fully functional neural network from scratch. So first things first, let me just quickly import the dependencies that we need. So let's say import numpy as np. So numpy is basically the only dependency that we require to build this neural network. And numpy is a great library. I love numpy. NumPy helps us do a lot of scientific computing and stuff. So go check out numpy. And yeah, basically NumPy is the only library that we need for this neural network. So so yeah, in order to build a neural network, we need the input data. So let us quickly build the data set for our neural network. So we can have something like a pair of values, like one value shall be the number of hours sleeping, and another can be number of hours studying. So the output of these values can be the test score of a student, right? So we can let me just quickly comment that out. So I like to keep my code clean and very descriptive. So we can say hours sleeping, comma, another value can be hours studying, right? So yeah, that's going to be our input data, and our output can be the test score of the student. So yes, we'll just quickly define our input and output. So x equals our input is a numpy array. So you can say numpy.array, and you just define your values here. So it's a list. So you can say 2 hours of sleeping and 9 hours of studying. That can be one example, and another training example can be 1 hour sleeping and 5 hours of studying, and another can be 3,6 or anything. You're just making your training examples, and we can just set the data type to be float. And similarly, we need to also build our output data set. Output for these corresponding values. So this is like for if the input is 2,9, what should be the output? So it can be 92 is the test score, and 86 for the second example if it's 1,5, and if it's 3 hours of sleeping and 6 hours of studying, it can be something like 89, and so on. So we have defined our training data set, and what we can do is we want the neural network to predict these values. These values are right now they are continuous values. There is no way of telling them that the maximum of these values is 100. So what we'll do is we'll make the neural network predict a value between 0 and 1. And that value can be so if we divide these values by 100, it's going to scale down to a scale of 0 to 1, so that we know that 1.0 is going to be 100 and 0 is 0, and so on. So similarly, we can also scale the input values by dividing these values by their maximum. So for the first column, it's going to be all the values of the first column divided by the maximum of that column. So we'll see how we can do that. So we'll just scale the units, and we can say x equals x divided by np.amax. So it gives the maximum of each and every column. So we can say x. So and we can also specify the axis. So axis is going to be the column. So we can also do similarly the same thing for our output. So we can just divide it by 100. So you can say that the maximum test score is 100, and that's the reason we're doing this. And here the maximum of the input array, right? So maximum of the input array, and So yeah, we have everything in place to feed our neural network, and if you want, you can just print out these values and see for yourself. So print x and print y, and just quickly run this thing. It's only 2 non-keyword arguments accepted. I don't understand. So hold on. Non-keyword arguments accepted. Yeah, I just forgot a parenthesis here. So this input matrix should be enclosed within parentheses. So yes, that should be fine. So as you can see, this is the input matrix. So it has these values. Of course, we have defined it to be 2, 9, 1, 5, and 3, 6. So if you just take a look at the first column, it has 2, 1, and 3. The maximum of this column is 3. So if you take 3 and if you divide 2 by 3, it gives you 0.6. And similarly, you can, if you divide 1 by 3, it gives you 0.3, and if you just divide 3 by 3, it's 1. And for the next column, the maximum is 9, and if you divide 9 by 9, it gives you 1. And if you divide 5 by 9, it's 0.555, 5, and 6. And if you divide 6 by 9, it's this value. And so by dividing it by 100, we have just converted the output values to a scale of 0 to 1. So it's just a number between 0 and 1. So it's 0.92, 86, and 89, and so on. So we'll just get rid of that quickly. And so yes, with our input, with our training data set in place, we'll build our neural network class. So we can say class a neural network. So we'll just put object in there, and we'll just define a couple of before defining a couple of helper methods and functions that we require to propagate through the network, we'll just do stuff in the init method. So init is just like the constructor for the class. If you come from object-oriented background, you're from other languages like Java or C#. So we'll say parameters. So there are going to be 3 attributes, and to be precise, there's going to be the input size, output size, and the hidden size for 3 different layers of our neural network. So we can say input size equals 2 and output size equals 1, and so we'll just see in a minute why these size are what they are. So output size is going to be 3, and we need to also have weights for our inputs. So we can say weight 1. So we can have something like W1. So if you know backpropagation, so in backpropagation algorithm, we just assign the weights randomly at first to the input, right? So using NumPy, we can generate random values. So we can say random, and you have to mention the dimensions of the matrix that you want. So if for the input from the input layer to the hidden layer, it's going to be a 3,2 matrix. So it's hidden size to output size, and for the when the input is being passed from the hidden layer to the output layer, it's going to be a 3,1 matrix. So that's why we use this input size, output size, and the hidden size. So for W1, we'll say dot input size, comma hidden size, right? So I'll just quickly write the comment down. So it's 3 times 2, 3 into 2 weight matrix. So yes. And it's going from input to hidden layer, right? So we can similarly define the second weight matrix. So we can say random.random, and this can be of the size self.hidden size to self.output size. So and this will be a 3 into 1 matrix, 3 into 1 weight matrix, and it's from hidden to output layer. So course, you know that we have three different layers. One is the output, input, and the hidden layer. So yes, we have all the attributes in place. Now we'll define a couple of functions that we need in order to propagate through the network and make our network train on its own. And we'll have a couple of helper functions to help us get values for activation function, so on. So first function that we'll define is FeedForward. So FeedForward will just take the self by default and one argument, that's the input matrix. And so I'll just quickly write down the comment what it does. It basically does forward propagation through the network. Right, and we can say three different layers. So the first layer can be Z. So Z, and the input layer is going to be the dot product. So basically when you give the input values and you have the weight matrix, then you just multiply both the matrix, right? So that's what the first layer is doing here. So we can say using np.dot. So dot is a function from NumPy that helps you multiply two matrices. So you can say you can get the dot product of the input matrix and the W1 matrix, which is the first weight matrix, right? So just in case, I'll just write down the comment for that as well. So dot product of X, which is the input matrix, and first set of weights. Yeah, this is the first surface, which is a 3 into 2 matrix, right? So then we have the second layer, which is just simply our activation function. So if you know backpropagation, there are different kinds of activation functions that we can use. So in this example, in this implementation, we'll be using just the sigmoid function. So sigmoid is just a function that just takes a number and turns it into a probability, a number between 0 and 1, right? So we can say self dot. We can write a function sigmoid. So we'll define it later on, or we'll just define it first. So we can define sigmoid function, and it takes one number as input, and you can have something like derivative equals false by default. So I'll just tell you why we are using this derive parameter in a moment. So we can call if derive equals true, then return s into 1 minus s. So if it's not true, then we'll just go on and return the just the sigmoid value. So it's 1 divided by so just put it into parentheses, 1 divided by 1 plus np-exp, that's the exponential raised to the power of the negative input, the negative of the input, right? So I'll just explain why I use this derive parameter in a moment. So just focus on this step. It's this is the sigmoid function. So it's it takes a number and turns it into a probability. That's any number between 0 and 1. So yeah, that is in place. We can use this sigmoid function over here, and we can pass z. That's the first layer. So that's the input matrix multiplied with the first set of weights, right? And that is going to be our activation function. So then we have the third layer, which is just a dot product of the second layer, the output of the sigmoid function, and multiplied with the second set of weight matrix, right? So it's going to be no, it's dot product of the second layer and multiplied with the second set of weight matrix. So I'll just quickly write it down. Dot product of hidden layer. Hidden layer is the Z2 here, and second set of weights. So if you're confused what's the dimension of the weights, I'll just write it down. It's 3 into 2 here, and it's 3 into 1 over here, right? So that being said, now we'll take our output equals the sigmoid of the of Z3, of the third layer. The sigmoid of the third layer is our output. So we can call the sigmoid function again, and we can just pass Z3, right? So Z3, and from the feedForward method we'll just return output. So we just return output. So our function is laid out to forward propagate through the network, and yeah, in backward propagation you use the derivative of the sigmoid to find the slope, I mean the tangent of the slope. The derivative of the sigmoid function is s into 1 minus s. So whenever you're calling this function, if you set the derived parameter to be true, then it's just going to give you the derivative. So that's why we have used this parameter derive equals false by default. If you just call this function just like this, passing just one parameter, and if it's false by default, it's just going to return the normal sigmoid value for your number. Right, so now comes the main function that we can define. We'll define it below here. So we can define backward propagate, or we'll just call it backward. So it takes the input matrix and the output, desired output, and the actual output matrix, right? So yes, and yeah, we'll just write down the comment what this method is doing. Backward propagate through can't type through the network. So the main intention of doing backward propagation is to calculate the sum of the squares of errors and then minimize it. So error is nothing but the difference between the desired output that we require and the actual output that was predicted by the network, right? So we can say something like self dot output error. So what's the error? So what's the difference between the predicted value and the actual value that we require? So it can be the output, the desired output minus the output. So here, just don't confuse between these two things. Y is actually from our training set, which is here. This is the output that we want. If the input is 2,9, we want the output to be 9,2. And output is the values that are predicted by our network. So if we take the difference and store it into, we're taking the difference and storing it into the output error variable, right? Or we'll just comment it just for the sake of it. Error in output. Yeah. So then we calculate the delta of error. So delta is nothing but you multiply the difference of the difference in the output error and with the derivative of the sigmoid. So we can do like a self dot outputs delta equals self dot output error, and you multiply it with this sigmoid, the derivative of the sigmoid. So you can pass an output and derive equals true. So you take the sigmoid of the output. You don't take the sigmoid, but you take the derivative of the sigmoid. So and you multiply it with output error. That is going to give you the delta of the output. Right. So yes, and that's done. So we'll calculate the error and delta similarly for the hidden layer. So hidden layer is Z2 in our case, and Z2 error is going to be so it's going to be the output delta multiplied with the transpose of the second weight matrix. So it's self dot output delta with dot product with self dot second weight matrix and dot t. Dot t is just nothing but it's an attribute that gives you the transpose of that matrix. So self dot w2 is a second weight matrix. So it was of 3 into 1. So dot t will give you the transpose. So it's going to be 1 into 3. So similarly, you can calculate the delta for the hidden layer. So Z2 delta equals, you can multiply the error of the hidden layer and multiply it with the sigmoid similarly, or the derivative of the sigmoid to be precise. Yeah, and you can pass in Z2 here and derive equals true. Right. So if you're confused with what exactly this hidden layer thing is doing, so I'll just write the comment down in order to be more descriptive. So Z2 error, we are calculating this error in the hidden layer here, and so we're just basically determining how much our hidden layer weights contribute to output error. So this is basically coming from the chain rule of calculus. If you know how to do partial derivatives, then yeah, this is by applying chain rule, right? So if you don't know what's chain rule and what's partial derivatives, just go through the concepts, the mathematical concepts of calculus, especially this derivatives, partial derivatives, and the chain rule. How to use chain rule to find this out, how much our hidden layer weights contribute to our upper layer. I'm sorry, just Control Z. Yes, and then yeah, in this step we are just applying the derivative of the sigmoid to the error. So just applying derivative of sigmoid to Z2 error. Yeah, right. So it's similar to what we did to the output and output delta. So that's there, and yeah, once this is done, we'll just update our weights. So we can say self.w1 is our first weight matrix. Like we'll just add to it. We can just take the transpose of the input matrix and multiply it with the delta of Z2. So basically we need delta in order to calculate how much of weight to add. So we can say the transpose of our input multiplied with delta of Z2. So it's Z2 underscore delta. And so what we're basically doing here is we are adjusting first set, that is from the input to the hidden layer weights. The input to hidden weights. So the first set of weights is the weights for the input layer to the hidden layer, and the second set of weights is for the hidden layer to the output layer. So we'll just say Z2 and take the transpose and multiply it with the output delta dot output delta, right? So here we are adjusting the second set of weights. All right, second set which is from hidden to output layer to output layer. So I know you guys are loving these comments because it's so descriptive and easy to understand, right? So yeah, that is it. That is all our backward propagation method is. So we just called the function backward. I don't know for what reason we called it backward. So that is what does our backward propagation for us. So we'll just quickly define a method that would train this, like to invoke this backward propagation method. And so we can say self, pass in the input matrix and pass in the output matrix that we require, and we can just say output equals, we can call the forward method, it's actually FeedForward. Yeah, FeedForward, and we can pass in the input. So we can then call backward. After the FeedForward is done, we can call backward with our input matrix, our required output matrix, and our output, right? So yeah, once this is done, we have defined the class for our neural networks, and we can just create an object. So we'll call it nn equals create a new instance of this class, and So for this example, we'll just take 1,000 iterations. So for I in range 1,000, so it's going to go 1,000 times. So it trains the neural network 1,000 times, right? So yes, and we can just call on the train method off of this object. So we can pass in x and y. Yeah, x and y. So once the training is done, we can just print out the values for our loss and the actual output if we want, and the predicted output. So we'll just print out the predicted output now. So we'll just print predicted output, and just we'll just get the output of the forward function, FeedForward. So or we'll just convert that matrix to string, just in case, if it needs to be converted to string. Right, close another parenthesis right there. Yeah, so this is pretty much done. So we'll just run this neural network and see if we have any errors. I'm pretty sure this won't compile, because I'm pretty sure this has at least 1 or 2 errors. So yeah, we'll just run it. Yeah, so luckily we don't have any errors in any kind of syntax or semantic errors. So we have this predicted output after 1,000 iterations. For the first output value is 0.90, but it was 92 or 0.92. So yeah, just to be sure, just to be more verbose, we'll just also print out the input and other stuff, the actual output that we require, and compare the difference. So we can say input string of x. Yes, that's the input matrix. We can say this is the actual output. So we have the predicted output, we have now the actual output, right? So it can be the y matrix, right? And we can also print our loss, so how much loss is incurred in our predicted values. So that can be, so you can calculate loss by taking the difference between the actual output and the predicted output and squaring it, and then taking the mean of that whole for all the input values. So it's pretty much np dot mean gives you the mean of a set of values, and you can say you can square. There's also square method from NumPy. You can pass in. Now you can take the difference between y and so the predicted values is what's returned by the FeedForward method, right? So yes, and you can just put it into the string method. Yeah, so that's our loss, and yeah, we'll just print another new line before we actually print out the output. So yes, if we just run this all, so you can see here the input matrix was 0.667 and 1. So these pair of values were the input matrix, and the actual output that we require are 0.92, 0.86 and 0.89. So after 1,000 iterations, this is the amount of loss, and the predicted output is, it's pretty close to the actual output that we require. So it's 0.90, it's pretty close to 0.92, and it's 0.879, which is just slightly above 0.86, and 0.889, so just slightly below 0.89. So it's close to the actual output that we require. And another thing that you can do is you can also print out this print out the loss every time the loop reaches 1,000 or 100 iterations, right? So hold on a second. So just print out. So we'll print it out every 100 iterations. So if I modulus 100 is 0, then we print the loss, right? Yes. So as you can see, at first the loss was 0.000895, and after another 100 iterations it's 0.00075, so it's gradually decreasing, so as and when we train. So if you just increase this number of iterations, it will be more accurate. So that's all for this video and the implementation of backpropagation for a neural network in Python. So if you have any doubts or any queries, just leave it in the comment section below, and I'll just give the link to the code in the description below, so make sure to check it out, and change these input values, and also make sure to play with this range. So just 1,000 iterations in my case, so you can just change it to whatever you want. And yeah, that's it for this video. I'll see you guys in the next video. Till then, take care. Bye bye.